it differentiates it, and once it has the output, it goes to a digital to analog converter, back again, and then he feeds it into the input from for the closed loop system. So this is, we will eventually touch a little bit upon this digital controller, but this is basically the difference, right? You replace all these analog networks, you replace them with a processor, right? All right, so this is what we will be doing in the class. Eventually, first of all, we're gonna be studying this from using MATLAB. We're gonna be simulating this thing so that we can understand the basic principles that are required when you are dealing with this kind of systems. And eventually, when we get to the lab, you will get a physical understanding of this because you will get to apply them using the cables and seeing that it actually behaves the way you're supposed, or the way the MATLAB simulations tell you it's supposed to behave. This is why this is a really cool system. It is a very basic system, but do not think that this is just something that we are studying because it's just easy to do. I mean, this is the basis of a lot of systems in real life. All right. So all these principles for the PID controller are universal. You can actually apply them to more sophisticated looking systems. For example, before we move on to a MATLAB refresher, which is what I want to do today for you, I need to do a MATLAB crash course because some of you, will complain, oh, I forgot MATLAB, I don't know how to do it. So I will give you code that you can use as a skeleton for you to produce your simulations. So I will do that in a moment. But before we move on to doing something to do the MATLAB code, let me show you this video that I found on YouTube. Let me just set it up. Are there any questions up to now? Any comments? Just give me a moment here. I'm trying to set this up. I need to get all of all these ads that you get in the on YouTube, right? All right, so it's ready. Let me just share this. This is just to give you an idea of the range, or the dynamical range that you can actually achieve when you use a PID controller. So that you can actually see that this is not something just to entertain us, right? To let me try to see here. All right. So this video is called Ball and Plate PID Control with 6DOF Stewart Platform. This just stands for degrees of freedom. Maybe you know what that means, maybe you don't. I will not explain right now. We don't need it. We just want to see what this system is doing. And if you know nothing about this, and if we just can you guys hear the audio? Is the audio coming through?
Yes.
All right. Let's just look at what this thing is doing. All right, I think I can stop it there. So what are we seeing here? We have this plate that somehow interprets the position of this ball, and the goal of this system is to center this ball right here at the very on the middle of the platform. And you can see as the person pushes the ball, it goes away from the center, and the platform adjusts itself so that it can actually bring it back to the center. So these are just basic control principles, right? And if you look at the code of what this guy's, I think this is an Arduino. This thing is right here, right? I think this is an Arduino. So this Arduino is generating the signals and it feeds it into these servo motors. Maybe you guys know what a servo motor is. So this is a bunch of servo motors connected to the platform. The PIC is just sensing whatever this platform is sending as digital data. It processes it, it interprets it, and it generates a control signal using a PID controller so that it can move around to eventually stabilize the ball at the center. So you looking at this without any kind of understanding of these feedback principles, you may say, "Oh, this looks very difficult," or you know, or something I may not even know how to do. But you will see in this course that these things are, all you really need to do is understand the basic principles behind feedback in a physical sense, right? Because we're not going to be discussing the root locus or body plots or Nyquist plots or any of these fancy tools that you learn in EE371, which you still use because this is a linear. You eventually deal with a linear system. But if you understand PID controller after you take this course and you go back and you look at the documentation behind this, building this system, you will see that you will actually understand what is happening, and you may even, be able to implement one of these things on your own, right? So notice how this system looks very different from the motor that we will be focusing on in this class, but it eventually boils down to using the same principles and understanding what thing you are trying to control, which is a physical system here. This is a heavy ball. It has inertia, right? And this is what most you will fight against when you're trying to control these things. In a similar manner, the motor that we are trying to use here is a physical system, right? This thing, this schematic for the motor, which is right here. This is the motor. It has inertia, right? I mean, it has a coil inside. This thing weighs, right? I mean, it has weight, right? So therefore it has inertia, and this is what you're trying to fight against when you deal with control systems. All right. That video is interesting, right? I mean, probably some of you have seen it already, but this is what you will be enabled to understand after you go through this course. I mean, if you put in the effort, that is, right? All right. So I think I've said somewhat enough about as an introduction for the course, as an introduction of what we will be doing. So are there any questions right now? Pretty cool, huh? This is this is something that, really gives you an understanding of what problems are outside, because this thing is a highly nonlinear system, this motor, even though it looks simple to understand, and you will see you will be asked to derive the equations of motion. What does that mean? The equations that describe the behavior of this motor, you will be asked to derive them in assignment number 1. And you will see that you can eventually boil this down to a second ordinary differential equation, which if you do the Laplace transform is a very simple, basic linear system. But this is just a simplification of what real life is. But you see, all these simplifications, these allow you to actually achieve some really cool thing. This system that I just showed you on the YouTube video, this thing is a highly nonlinear system. Nonlinear systems are very difficult to even understand mathematically. How would you even attempt to control it if mathematics are just intractable? Well, you do a linearization of the thing, right? You try to understand very small deviations from a stability equilibrium, and then you see whether you can actually apply the linear techniques that you know about to control this thing within a very so that you can control it against small perturbations from the equilibrium point. All right, so this is what we'll be doing. This is very cool and interesting. So I think we should move on to MATLAB so that you can understand what we'll be doing, or I mean, in terms of the level of MATLAB coding that I will be asking you to use, or to the level of the commands. So this brings me to assignment number 1. This is the servo mechanism, equations of motion, and transfer functions. I gave you here a reference. You should read this on your own. I will not read this thing entirely, but I gave you here a reference which still works. I just checked. All right, so that where they actually show you how to derive these things, because in order for you to derive these things, you need to remember your Newton's laws, and the Kirchhoff's voltage laws. Some of you may have forgotten these, doesn't matter. I gave you this reference so that you can read through it and then come up with your own derivations for these equations. These equations are the same. You can use the same parameters that they do use in there for the inertia of the motor, all these constants that are specific to the motor. You can use the same value that they give you there. So essentially, assignment number 1 is getting you ready to actually be able to understand whatever pictures you get out of MATLAB. So this class will not be for me to teach you how to use MATLAB in a control in control theory. We will just use MATLAB as a tool for us to explore the very specific and basic principles of feedback. And in order for me to do that, I need to make sure that we are on the same page and you understand exactly the commands we will be using, so that you are not lost and then you don't come to me, complaining, oh, I never was taught this on, on MATLAB. I don't know what this command is. So that is why I will give you this crash course on MATLAB, so that you know what you will be expected to do. So in essence, assignment number 1 is you will derive some ODEs, ordinary differential equations, very simple ones. I give you the reference. You can just mimic exactly what they do there, and then just produce your own paraphrasing of what the derivation entails. In task 2, you will be asked to generate some step responses. I need to explain what this means. Some of you already know what the step response means in a theoretical sense, right? Because if you are at this level, you should understand what it means for us to generate a step response for this kind of system, right? But maybe you don't know how to do that in MATLAB. So that is why I will give you this short presentation for MATLAB. So this is what task 2 is about in this assignment number 1. You will first, in task 1, derive the ODEs, and then you will take the Laplace transform so that you can get your transfer functions. And then, eventually in task 2, you will do the step response. You will do the response to a triangle wave and to a sine wave. So this is what we are trying to do here, because this is what we need. Remember, I showed you this schematic of the motor, right? I mean, this is the best one. You have a function generator here. This thing generates sine waves, triangle waves, square waves. So this is what you generate out of this thing. You put it into the system, and then this behaves in a particular way. So given that you have derived the equations properly, whatever behavior you get out of the system should actually follow the real behavior very closely. And this is what you will actually see in the lab. So this is why we are interested in using MATLAB as a tool, so that we can actually generate the responses, so that we can understand how this, this motor fits into the general schematic of a closed loop control system. All right, so this is why we need step responses, we need square wave responses, sine wave responses, right? So notice I didn't say frequency response, right? Frequency response is where, what is a frequency response? Anybody remember? From EE 371 or Systems 2 or Systems 1. What is a frequency response? Uh-oh. Really? Nobody knows? Am I muted or something? Oh, I don't think so. Okay. Let's move on then. No frequency response. Okay, so we're gonna do some MATLAB plotting here so that we understand what we're trying to do. So I will start here with I think I'm not showing you this. I will show you a MATLAB script. So it's empty. We will work through these commands one by one so that you understand and that you can use this template, this code as a template or a skeleton for you to build up your own programs and for you to be able to simulate these things. All right, so the first thing I wanna, you can all see this, right? I mean, this is, all right, so just to guarantee that you guys have a clear, I mean, these are just some things that I usually put whenever I run a new program. These are not strictly necessary. These are just to clear the memory and to clear the output windows for MATLAB. So these are not any commands of big concept of importance for us. All right, so here we are. I think I need to see, I don't know if I want to show my full screen, but I think I should do that. All right. All right, so now you can see my MATLAB window right here. And now you can also see my my script. All right, so that's where we are. So now, first of all, let us try to see whether we can generate square waves and triangle waves and sine waves using MATLAB, and whether we can actually get to show them in a nice way, because we're going to use these things. So these are the first things we're going to try to generate. If you remember, you use these symbols for comments. So we're going to be generating simulations. So let us allow, or let us define our maximum time for the simulation. So I will say max simulation. You don't have to worry about writing anything down, or any particular commands that I use right now, because I will email this to you. What you do have to do, what you actually must do, is write notes to yourself as to why I'm doing this or why I'm writing these lines, right? So that when you actually get to write them on your own, you understand why you need these things, right? So don't copy any commands, or don't worry about this, getting all the details that I will type in here. Just, worry about getting the general idea of why I'm doing this, right? And to help you do this, make sure you see that we have the line numbers here, right? So that you can actually write down these notes down. I will try not to modify this when I email this code to you, so that when you do receive it, you actually can map your notes to the actual code, and you understand why we had this in the first place. So I just want to set up a max time for the simulation, nothing else. So I will just define this as this. Let us do some 2 pi. So this is almost just a little bit above 6, right? 6 seconds, 6 units, whatever you want to call it. So now we need a time vector. Notice I'm going from the very beginning, because I want all of you to be on the same page and understand why we need these things. So now we need a time vector. We're going to define it. We're going to start from 0, and then we're going to go in steps of 100. So like that, and then we use the T max. Of course, you all know by now how to download MATLAB on your own computer. You do not need to pay for it. As a student of CCNY, make sure you go through the correct website online, so that you can install this software in your computer. You do not have to pay for it unless you want to, right? So now notice a cool thing about this newer versions of MATLAB. When you click on a variable that you have previously defined, it highlights all of the previous variables, so you know where they are. So for example, when I click on this T max, I know where it was defined in blue, and I also can see this right here on this line markers here. These little things that come up when you click on these. This is very useful. You will find when you have so many lines of code here, and you want to see where the definition was, or where the other instance of this thing was. That's pretty cool. So now another thing you can do, for example, suppose I don't like the name of this thing anymore, right? I want to change it to something else. Let's say Tmax 1. So you see, I just changed the name of my definition, and if I press Shift Enter, it will change the name of all the other instances in the same code. So this is something that you may like to be aware of, so that you can use it, right? These are pretty cool, simple little neat tricks that you can use to make your life easier while coding in MATLAB. Let me revert back to this. All right. So this is our time vector. This is how many points our signals will have when we actually plot them. I will go back to this because this is very important. All right. I want to generate a scalar. So I want to do some scaling for the frequency here. So I will explain what the meaning of this is. So I will put scalar equals 1. I will explain this when we actually get a plot, right? So that you can see. All right. So the first simple thing that we can generate is a square wave. So how do we do that in MATLAB? Well, let me just define this, give it a name so that I can store this. All right. Before I do that, let me just run this code. Okay, so I ran it, right? Remember the semicolons here, if you put them here, it will not show anything on the output command window. But if you remove the semicolon, for example, if I remove the semicolon from this scalar, and if I run the code again, it will show the scalar on the command output window. So whenever you want to see things on the output window, you remove the semicolon. Otherwise, you leave it in there so that when you run it, it doesn't show anything. By the way, how do you know whether this was actually saved and executed? Well, you look at the workspace, right? This is what the workspace is here for. We have a workspace. Here you can actually identify where your variables are and notice the difference of what the things we have created. Scalar and T max, these are just simple numbers, doubles, right? Now T, what is T? T is an array of numbers. This is what T has generated. Notice this is a row array, right? I mean, it just goes all the way up to 629, right? It's a lot of points. This is our time vector. So this is what we will use to run our simulations against, or the time that we will actually see in the simulation, so that we can actually know how many points we have in the vector. So this is how you do that, right? If you want to know how long this was, you can either use a command in MATLAB, or you can look at the workspace and see how long this is. And I highlighted the fact that this is a column or a row vector, right? Because it just occupies one single row. This is important because sometimes the commands that we use will either spit out a row vector or a column vector. And if you try to add them together, it will give you nonsense because you're adding two different dimensions of vectors, right? If I wanted to transpose T, how would I do that? You can do this in a very simple way. T equals T apostrophe, like this. This is the transpose, this thing. So if you do that, it will generate a column vector now. Notice how if I go back to the workspace, it says now that this T is 6 to 9 times 1. That means 6 to 9 rows times 1 column. So we have now essentially a column vector. You have to be aware of this difference because MATLAB will not give you an error message. It will not catch this error if you try to add them. It will just do that, but it will generate something that you do not expect to receive. All right, so when you do this, make sure you understand whether the vectors that you generate are either row or column vectors so that you can actually understand what you are doing. All right, back to the square. So this is the name that I will assign to my square wave. So this will equal square. This is the command that will generate a square wave for you. So square is the command. So now let me write this in this way. Scalar times 1. I mean times T, right? So what have you done here? You have taken the T vector, the time vector. We have scaled it, right? Since this scalar is 1, this will just be the same thing, right? This thing is just equal to T. And then when you use this command, it will generate a square wave whose time axis is as long as T is, as this time vector is. So now let us try to see whether we can actually show it. Figure 1. I'm doing this for a reason, right? So that you understand what you are doing when you are plotting these things. Now, so I want to plot this thing. So I want to do T, comma, square. And I want to make it pretty so that we can actually see it, so that we can actually understand what this is. So I will not explain how or why this is. You can actually see this on the reference from MATLAB. Well, this thing that I just put in here, this highlights that this thing will be red. And I want it to be a little bit thicker so that we can actually see it. So I will do line width. Again, you do not need to understand these commands right off the bat. You can just use them because you will receive this code on an email from me. You can just use them whenever you plot your own responses. Just understand why they're there, right? You do not need to understand the whole detail behind these things. All right, so let us run this and see whether we can get something nice out of this. Oh, look. It looks like a square, right? So just Now there's something off is, you know, there's something off in this picture, right? Which I don't like, and which I would love for you to notice when you are plotting these things, right? So that you can get nice plots, which first of all, by generating nice plots, you will be actually able to you will be in a better position to understand the behavior of your system. Because if you have really rudimentary plots and you can really see the images or the signals, then it will actually not help you understand whatever you are trying to study, right? So that is why I'm emphasizing generating nice plots so that you can actually see what you're doing. And I'm giving you the code to generate nice plots so that you know how to do it, and you don't have to go online and start finding out these things. I'm just going to save you a lot of time doing this for you. All right. So this is all you can actually put in here, right? So let us try to put in a legend so that we know, even though we only have one signal here, let us just get ready for the legend, because we're going to plot a lot of things in the same thing here. So square. So that's correct. Now title, because we're gonna plot several things here, I'm just gonna call them waveforms. So X label, this is just the X-axis, right? Time. Y label. This may be, some of you may already know how to do this. So I'm sorry if this is a little bit boring, but I need all of you to be on the same page. So this is, I must do this, all right? So just bear with me if this is, you know, too basic for you. I want to have a grid so that we can have something nice to reference if we have to. And then axis. Oh yeah, why am I doing this thing that this axis is important? Notice how when I plot this thing, MATLAB just stops plotting at some point, right? I mean, this is 2 pi over here, right? Well, then MATLAB gives you all this empty space here. Why would it do that? I mean, this is something you can actually control, right? I mean, you don't want to have empty spaces after, you know, this looks weird, right? It looks incomplete, right? So you can actually fix that by, let me just show you, by specify an axis for the window. So you do 0, T max. This is the X interval for the time, and for the vertical grid or the bounds, I will do 1.5. This is just an arbitrary number that makes this thing look good. So let me just run this. So this is, again, this is for the X interval for the X axis. These are the bounds. So because my vector times at 0 and it ends at T max, I want the plot to start at 0 and also end at T max. So that is just nice within the window. It's nice and flush with all the data inside the window. And this is just the vertical bands, the vertical bounds going from minus 1.5 to 1.5. So let me just run this again and show you what. Now look at the difference, right? We have a signal that is well within the window here, no empty spaces here, and it is like centered, right? You can actually, I'm sure you can all appreciate the difference, right? If I run it without the thing, look at this, right? I mean, it doesn't look very good. You know, what bothers me is that, you know, this thing is like clipping too close to the edge here. So we can really see this. And when we have a lot of signals here, this will start to make cause trouble. So that is why we want to eliminate all of this. And if I uncomment all the things that I just wrote, hopefully it doesn't give me a complaint. Here we go. Notice we have a time vector, an amplitude, we have waveforms, we have a little legend here, and we have our square wave. Now let us understand what this scalar means. Can anybody say what would happen if I make this 2? What would I expect the output to look like? I mean, I have a hint here, right? If I make this 2, what would you expect the output to look like? This is one cycle of this square waveform, of this square wave, right? This is just one cycle.
It would be twice as long, Professor?
Yeah, I mean, not twice as long, but I mean, yeah, I mean, the time vector would be twice as long, and you would see two periods of the thing, right?
Right.
All right, look at this. So instead of changing, right, the the time vector here, right? You can actually scale it in an easy way so that you can decide how many cycles to show, right? Inside the window here. All right, so this is the point of scaling, of frequency scaling, because this becomes useful when you have more signals and you want to change the scaling of these things, right? So let me just revert back to, I mean, 2 is good, right? 2 looks good. Why does 2 look good? Because we can see the periodicity of this thing, right? We know that we have some periodic behavior here. So this is another thing. If your waveform is periodic, you cannot just simply show me some one cycle and expect us to believe that your signal is periodic, right? What do? You allow enough time or enough frequency so that we can actually see that the signal is periodic. So in this case, we can most likely assume we can be sure that this thing is periodic. So this is okay. All right. What is another thing we need to know how to plot? Triangle waves. All right. Triangle equals. Now, there's no command for triangle. What we have is sawtooth. So scalar T. So what makes it a sawtooth? For example, let me just plot it, right? See what we get. So that you can see the difference between, so now how do I do this? All right, I will copy this. Okay, so I will plot it here, triangle, and let's make this green. And in the legend, I want to include a triangle legend. Why am I doing this? Because in the same plot, you will actually be required to plot several waveforms. So you need to have a legend so that you can easily differentiate them, right? In this case, it may be trivial to have this because we, of course, can differentiate a square wave from a triangle wave. But when you have your simulations in for the actual several mechanism, you will only have inputs and outputs, right? You will not be able to more or less you may even have several responses in the same waveform. So how would you distinguish them if not using a legend, right? So let's just try to plot this and see what we get. I mean, this doesn't look like I mean, it looks like a sawtooth, right? Which is what this command promised you to have, but it doesn't look, like the nice 50% duty cycle triangle wave that you were used to, right? So how do you adjust for this? You go into the sawtooth command and you introduce a new parameter, this duty cycle. So this is 0.5, which stands for 50% duty cycle. So if you run this again, it will give you this, a nice centered triangle, which has a 50% duty cycle. All right, so we're good. I mean, we're producing nice pictures here. So this helps us understand what we are doing here. So now the final signal that we will need is a sine wave. All right, sine equals all right. So that's did I write this properly? Yes, I think I did. All right, we need to do this so that we understand what's coming next. Oh, what did I forget? The legend, right? All right, so let's just sine wave here. All right, so we have nice plots here now. Look at this. We can easily tell. I mean, of course, it is very easy by inspection. Just looking at these things, we know which one is which, but eventually you'll have so many weirdly varying signals that you will not be able to distinguish them just by looking at it, right? So that is why we have a legend. You can choose the legend to be something else if you wish to. You can have little markers here, whatever you want to do, as long as your plot doesn't become just too convoluted, right? Too full of things, unnecessary things that it defeats the purpose of actually cleaning this up. So we have a title, we have amplitude, we have time, we have a nice window, everything is centered, right? So now let me explain this time vector here. Why is this important? You need to allow your plots to have enough points so that they can become nice smooth waveforms, right? What happens if I make this 10, for example? I mean, instead of going in intervals of 100th, what if I go into, in intervals of tenths? Let's just plot this. I mean, you cannot see very much of a difference here, but although, if you look at this closely, you should start seeing something. Does anybody notice something here? I mean, look at this peak of this triangle. It isn't as smooth as it was before, right? Because you have fewer points now. There's something more subtle about the square wave that you cannot really see unless you actually look at it. Can anybody point to me what is the problem? What the problem may be with a square wave that we are seeing here?
The line is. Go ahead.
The vertical lines aren't exactly.
Yeah,
vertical.
this thing is slanted, right? I mean, there's a kind of a slope here. You don't want this to happen in your simulations because it will just throw you off. The fewer points you put in the MATLAB plot, the less smooth your waveforms will look like, and then it will give you really bad simulation results. So if we make it even smaller, I mean bigger here, and look at this nonsense. Now we can actually see that this is just nonsense, right? Because why is this happening? Because you are not allowing enough points in your time vector. So the waveforms do not come out to be as smooth, and they do not look anything like what they are supposed to be. None of you would come in here and tell me that the green one is a triangle wave or that the red one is a square wave. Whatever that is, we don't know what it is, but it definitely isn't a square wave. And this is something you need to watch out for, because if you put this kind of signal into your simulation, it will give you garbage. And then you will be trying to explain some weird things which could have been avoided by just putting in the right inputs. So you guys can see that we're not just wasting our time here. I'm doing this for you so that you understand how much, what to do whenever you encounter these kind of situations, right? So now if we go back to our resolution, this is the resolution, right? So if we go back to our 1/100 resolution, we have nice vectors here. Of course, the bigger the number you put in here, the smaller, the finer the resolution will be, and the more points you will have here. And probably MATLAB will not complain, but it will make your plotting a little bit more slower because you have more points to compute, right? Of course, you're not going to go here and make it 1,000,000, right? Because that would just be overkill, right? So there's a nice, sensible way for you to find out what this is. This is a good number to start with, assuming this Tmax isn't very big, right? If this is 1,000 and then you put something big right here, then it just defeats the purpose of doing this thing, right? So make sure you watch out for this, right? You may have to adjust this resolution when the time comes, right? So any questions so far? All right, let's get into responses. We haven't done any, so I will not mess up with the I can't see from here. This thing is in my way. All right, so let's go into responses now. I like to define the Laplace variable using this command so that we don't get confused. You don't have to necessarily do this, but you can just run with this. This is just the Laplace transfer because we're going to be generating our transfer functions that we want to get the responses of. So let us just start doing this. I have defined here my Laplace variable, the S. Oh, I ran the code. I shouldn't have done that. I want to comment this out so that it doesn't keep coming up whenever I run this again. All right, so let us compute the response to one of the very simple transfer functions that we know very well. So let me just set up here some preliminary values that I need. So I need a gain for my transfer function, and I need a time constant. This will make sense when you actually see the plot or when I actually write down the transfer function. So I need a small time constant, which is tau. We're going to call it 1/10. Probably some of you already know where I'm going with this. I want to show you the response of a very a transfer function that you are all very well familiar with. So this is my transfer function now. Lag TF. TF stands for transfer function. I want to keep my labels correctly so that I can plot them. And this is also this is some kind of this is something you should also get used to, labeling your things properly so that you don't get confused as to what they are, right? Looking at this, I know exactly what this is telling me. This says the lag network transfer function, right? So let me define that as 1 plus tau times the Laplace variable. Does anybody know what this is? This is just a gain of K1. So this is 1 over plus 1 plus time tau times S. What is this thing here? I'm sure all of you know what this is. All right, let us proceed. Let me compute the step response for this thing so that you know how to do it at MATLAB. So step response lag equals step lag TF comma T. So what this will do for me is it will take this system that I previously defined over here, right? The lag TF, and it will compute the step response to this using this time vector as a reference. So it will give me as many points as I have in my input time vector. All right. So if I run this,
Professor, I think you made a typo.
Uh,
You wrote lag FT right there.
Yeah. Thank you. That is why it wasn't turning on, right? This thing, yeah. Thank you very much. Eventually, when you run these things, MATLAB tells you that there's a mistake, right? I mean, I'm just typing this, you know, off the top of my head. So I may make some small mistakes here. So let us see the response here. Can we see it? So let us create a new figure 2. So now we plot T comma, what should I put in here? Step response lag. What else? The nice I should just copy it from here. All right, can I get something out of this? Will this give me something useful? Let's see. Here it is. Does anybody recognize this thing? Well, what is this? This is a low pass filter, right? 1 divided by 1 plus tau s. This is a low pass filter, which is called also known as a lag network. Doesn't this look like the response of a time of probably if I put in the step, right? So this is the problem when you use the a command like this. This thing just computes the step response. It doesn't give you the output the input used for the computation of this thing, even though it is a step, right? It is a signal that goes from 0 to 1, and then it stays at 1. That is what a step is. So if we look at the plot from that we had before, we had a square wave. But if you take only the beginning of the square wave, that is what a step is. So this command is generating the response of this network to a step. Notice we didn't even have to put a step here or specify anything here other than the time vector and the transfer function that we are dealing with. And then this says step, it computes the step response. So we can really see much about this. So we're gonna generate these in a different way eventually so that you understand why we need to do this. But before I do that, I wanna create the counterpart for this one.
Professor, is it a low pass filter or a high pass filter graph?
Can you tell by looking at the response? This is the output, right? So imagine the step is the beginning of the square wave. It goes from 0 to 1 and it stays here. So imagine we had the input here at this corner, right? And you get this response. All right, let's play with this, right? Let's make this even smaller. You see how this resembles the square wave, the step even more? Because this is a fast time constant. It's very small, so the response of the system is very fast. So what happens if we make this bigger? 1 over 1, which is just 1. Look at this. Doesn't this remind you of the charging of a capacitor? Right? If the time constant is too big, you see that this thing takes time to charge up all the way to the maximum value, which is 1. If we make this even bigger, then you'll start seeing just very, very slow responses, right? Look, it doesn't even have enough time to reach 1, right? Look at where this goes. It goes a little bit past 0.7, right? If we could extend this time axis here even more, you will see that this would touch eventually, it will reach 1. But because this time constant is so big, then the response of the system is slower. If we want to make it faster, like I had before, 1/10, right? So this plot that you are currently seeing is 5. So this is 1. Notice how it'll get tighter and tighter to the step, right? So 1/10 will make it even tighter, right? Look at this. It reaches 1 much quicker than before. Now, if we make it 1/100, it'll definitely look. You see that although there's a little separation here, I mean, it isn't exactly, but it is very fast, right? If we make it 1/1000, you can't really see the difference between this output and the step. This is because the system, when it has a really low time constant or small time constant, it behaves very quickly like that, right? So it is able to sense or accommodate whatever input it has, as long as it is a step input, and it's able to mimic it very right away because of the time constant, right? So if we make it 1/10, so you who asked the question, is this the response of a low pass filter or a high pass filter? The person who just asked the question, can you tell me now which one is this for?
So it is a low pass filter.
Yeah, it is a low pass, right?
Yeah.
But are you sure of it, or are you just you know? Let me plot the other one so that you guys can see that we are not doing anything esoteric here. This is just something you are probably not, that isn't too fresh in your mind. So don't worry, we're gonna review this and we're gonna know exactly what is going on here. What is the difference between what I just wrote and this one? The numerator is different, right? We have a Laplace variable times the tau. Let's see what this thing does. All right, so we're gonna write lead. I should make it red so that we can see this, right? All right, is this okay? It looks okay. All right, let us see what this thing is doing. All right, here you go. Now this green, you can see that this is the output of a high pass filter, right? Because you know, you can think of the high pass filter as letting the higher frequencies go through and filtering out or stopping the lower frequencies. When does the high frequency input happen? When the input changes from 0 to 1. That is a high fast transition. So you can think of that as a high frequency signal. So it goes through. So you see this behavior in the green one. For its counterpart, you see the red one, because it is a low pass filter. It only lets the lower frequency signals through. So that is why you see it reach 1 for lower when the input has settled into the steady state, right? Anyway, I'm not going to do the pretty up stuff that I did for the other one, because you should be able to do it on your own now, right? So the only thing I want is this. For now, you can do the legend and the stuff here. You can do that on your own. All right, what happens if we make this scale or this is just the step, so we can't see this. So this is the problem. When you have the step, you can't really control this very much, right? I mean, you can't really see whether this is, you know, what this is in terms of periodic functions, because this is just a step. So what you do is you take the inputs that you generated here and you feed them into the transfer function using a different command so that you can actually manipulate them. All right, let me just show you what I mean by this. So this will stay as it is. Notice I didn't put the legend here, none of this stuff, right? I just left it like this because we know what we're gonna get a prettier image right now. All right, so let us compute the square wave response to this transfer function here. All right, so this is what you do. You write, let me just put the name, square response lag. These names are probably too long, but this is just a crash course. I want to make sure you see where everything is and why we are doing this. So I will just do that. So instead of step, we want to calculate a more sophisticated response to a more sophisticated input. So we use LSIM. This is the command you will be using over and over and over and over in this semester. So make sure you see why we are doing this. LSIM allows you to calculate the step response to a linear system using any kind of inputs that you can come up with. So this is the thing. This is the thing to use. Step will get you the step, quickly the step response to your system. And if that's all you care about, then that's good. But since we are looking for more sophisticated inputs, we need to use the LSIM so that we can generate the responses in a very easy way. So I can just do the same thing that I did here. Except, so I need the lag transfer function. And between the time vector and the input, you need to specify, the transfer function, you need to specify which input you are dealing with. So in this case, I want the square. So look at this. This is the lag transfer function, or AKA low pass filter. This is the square waveform. This is the time vector, and this is the LSIM command. So we have now this thing. So let us just plot this, see what we get. I want a nice legend here. I don't want to. All right, figure 3, plot t comma. This is what I want to plot. I will let MATLAB do the legends. I just want to just hang in there. I just want to. So legend. I want to let MATLAB do the colors of the legend. I just want to. So I will do it like this. All right, this is enough. I don't want to go through all this thing of making titles and none of this stuff, right? So I can get rid of figure 2. Not get rid of it, just comment it out so that it doesn't get produced every time I run this thing. Oh, look at this beautiful thing. Now it looks, to all of you like the response of a capacitor, right? Or a low pass filter. Remember, when you first met the low pass filter, you derived this thing from the behavior from the voltage across the capacitor, right? So this is just, we're going back to square one, except now I'm showing you how to simulate these things. So in the assignment, you will replace these transfer functions that I am creating with the ones that you will derive. So that's why we're doing this, right? So now, what else do I need here? First of all, I want to see the square as well over here, right? I want to see the responses to this. So the very first thing I should plot is the square wave triangle, the waveform, right? So I want to write the like this. So square n and square response. What does this mean? Square wave input, square wave response, right? Look at this. Magnificent, right? You have the blue input, which is the square wave, and then you have the response here. Notice if I make this a half, the scalar, notice here, by just me changing the scalar frequency, I was able to reproduce exactly the same figure that I got for figure 2. Look at this. Figure 3 are identical, right? You see how this orange is the response to the step, and this is the red one we got before using the step command. Well, now notice with the LSIM, we can control it. We can even plot the same input right here, right? So the blue one is the input. The output is the orange one. In this case, we're just showing 2 outputs here. So that is why you need to get used to plotting or using the LSIM command, because this is what we really care about. All right, so now let me compute this thing, the lead. So all I have to do is this, lead, it will give me my response. There you go. You see how easy that was? I just changed little labels here. So I will need to adjust this lag. There's a reason I keep calling this lag and lead. I mean, there's a reason for this, right? I probably should not discuss this right now. Look at this. If I adjust the scale to 2 cycles within the same time frame, you will see something that you all recognize or must recognize. Is this something you all recognize? If I make it 100, you should play around with this on your own so that you can convince yourself that this is exactly what you think it is, right? This is something you saw in lab 1, right? When you were doing these simulations in lab, I don't know what this circuit is software, right? You see here the time constant is so big that this network doesn't even have time to reach the maximum value here because the response is so slow. But if it is fast enough, right, it'll be okay. So the purpose of me doing this is that so that you know how to manipulate the inputs and what command to use when you are computing your step responses or your sine wave responses and all of these things, right? So in the assignment, once you derive your transfer functions, you will just play around with this by replacing this transfer function with your own transfer functions, and you will just follow the same schematic so that you can reproduce your responses. So what is left for me to do here? I should probably just show you this the responses for the triangles, and then you can do the responses for the sines on your own. Right? It's just we don't want to go through all this thing again. So I will just do it for you right away so that you can see once you get to do this enough times, you should be able to do this right away. So now we have the input set up, we have the receiving definitions here, and all I have to do is plot this again, figure 4, and now we will have a triangle, and then I can copy this. Oh, my mouse is just playing tricks on me. Here, you see how it lights up in blue? Because this tells me, oh, do I have a mistake here? Oh yeah. Triangle response. Yes. All right. So if I plot this figure 4, oh, I needed to change the legend. Here you go. Right? This makes sense. Does it? Let's see. Yeah, it makes sense. All right. So this is my crash course into all of this, because the main point is that you understand how to use the LSIM command. Eventually, you know, every time I introduce a new assignment, I will actually run the code in front of you so that you can see what to expect. And your task will really be interpreting whatever, you know, the assignment says, whatever the manual says, and whatever I say during the lecture, you know, processing this and writing a nice report out of your observations on the simulations, right? So you will never be left alone when it comes to MATLAB. I will be here for you to answer your question, all right? Like I said at the very beginning, and you should do that, right? The worst mistake you can do in this class is have questions and not ask them to me, right? That is not really good for you. So please do that. This is the last thing I needed to, I wanted to show you for this thing. You can make sure to produce the response for the sine wave and make sure you understand it. You can go back to this, play around with the frequency, the scaling, the time vector, the axis, and all these things so that you can be familiar as to how you can actually produce these things so that you can produce or generate nice looking professional plots, right? You don't want to just give me anything that just doesn't really make sense upon a simple inspection. Although this should really change to triangle, right? Triangle, the legend is a little bit off. So before everyone, I get, you know, I confuse somebody. All right, are there any questions about this thing? We have the triangle responses. We have the square responses. We're missing the signs. You can just do that on your own. I have figures too, which I commented out. Now, since we're done with this program, I can uncomment them. Now you can all see them all together, right? There's a way where you can actually have several plots on the same window. If you want to know how to do that, I can show you next time. If you don't, if you can't wait, you can just do it on your own. You can look it up on MATLAB. So here are all the figures that we generated, right? The the inputs, the step response, the LSIM response using for different inputs, right? So this is what I wanted to talk about. This should be enough for you to actually produce the simulations for assignment number 1, and this should really get us on the correct path to understanding the basic principles for control that we need in order to know what the PID is about, which is where we're headed. All right, any questions?
Yeah, can you open the schematic of the PID? I have a quick question about that.
The on the board that I showed you,
yeah,
thing?
Yeah, the board that you showed me.
This?
Yeah, you see how most of the operation op-amp over here are just a single input, but we usually deal with the.
I can't really hear you very well. Can you speak up or?
Yeah, can you hear me right now?
Oh, it's better. Can you? Okay, go ahead.
Yeah, I want to ask you, we usually deal in classes a 2-terminal op-amp, but in this schematics, all the op-amp are single input. So how do we know which input we are dealing with in this schematic and what input we are not dealing with? Is it the negative feedback or is it the positive feedback we are dealing with?
In this case, most of these op-amps are yeah, was somebody else, did somebody else want to comment on this? I heard somebody, these are inverting op-amps, right? What you're talking about is probably the referential op-amps where you see them inside, but most of these are inverting op-amps, right? Where you only need an input signal so that you can actually invert the thing, right? But anyway, this thing is grounded inside, right? I mean, we can't really see the connections in there, but it has 2 terminals, right? Except one of them is grounded to is plugged into a reference or a ground, right? So that you can actually invert these things. So these are not functioning here as differential op-amps, right? These are just functioning here as inverting op-amps that give you a certain gain. So that is why you do not need to worry about which input is which or which terminal it is going into, because this has been set up so that it functions as an inverting op-amp so that you can actually, amplify in a negative direction the input that is coming in. So you will not need to worry about whether this is going. You will just understand the basic operation of all these op-amps, which is depending on the feedback configuration, right? Because you cannot just put a signal into an op-amp like this, right? You know that. So depending on the configuration that it has on the feedback channel, it will behave accordingly. But these are all inverting op-amps. So there is no need to worry about which one is which or which terminal it is going to, right? And even if you want to go through that, if you want to, refresh, do a refresher on these things, there's chapter 1 and chapter 2 and 3, I think. Yeah, chapter 2. If you guys are interested into all these operational amplifier characteristics, you can actually read this. And this is a simple review of what you expect to see or to have as the output when you are using inverting op-amps. Notice that this thing will not go into the theory of designing these things. It will not show you how to, what's really inside, the transistors that you find inside op-amps. It will not do anything like this. It will just show you how you can actually, what it means to have these kind of components in the feedback channel for this. All right. So this is all you need to know. Notice how, as in your question, we only have one lead here. What does that mean? It just, depending on the configuration, it will either invert it or it will integrate it or it will differentiate it, depending on the component that you have on the feedback channel. But in short, you do not need to worry about this because most of these are just functioning as inverter amplifiers. All right.
Yeah, thank you.
Any other questions? I mean, this was good. I mean, we went through a lot of things that you need. This code is something that you will have to keep in. Where is? You will get this code from me. you should take your time to study this or to try to play around with some of the values here so that you see how things change. So that when we start actually doing our studies on the feedback principles, you can focus on the principles themselves, not be distracted by how you should plot this thing or that in MATLAB, which is not the point in this class. We are just simply using MATLAB as a tool to understand these concepts. And in order for you to understand the concepts, you should try not to be distracted by how things are plotted or what these commands mean. That is why I'm doing this for you, because most of the time you will simply be using this LSIM command, and that's it. All right, does that make sense? All right, so I think we're done here. But before you get depressed, before you get any kind of anxiety as to where this course is going, make sure you talk to me, right? If you don't understand anything in the assignment or the material, talk to me, email me, have a simple conversation with me so that I can help you get through this. This class is not complicated, right? It isn't, Borel sets or mathematical analysis. It's just something that comes from, has nice applications, concrete applications. And if you understand it, you will look at the world in a different way because you see how things work when it comes to these kind of systems with feedback. All right. I like this subject very much. If you want to talk to me about it, let me know. And unless there are any questions, are there any questions? All right, so I will see you next time according to the syllabus. Bye-bye.
Thank you, Professor. Take care.
All right, bye-bye.
Thank you.